The term heat exchanger basically denotes a device in which we have two fluids that don't mix. One is hot, one is cold, and the hot fluid transfers energy to the cold fluid. So this is a very quick, broad definition. What is a heat? Largely, you will see these devices being analyzed in a course in heat transfer, which is where you do the detailed engineering of what I did. That if I want to have 1 kilowatt heat exchange between this fluid and that fluid, how big a tube should I have? What should be its length? What should be the velocity? All those considerations will come out of the heat transfer course knowledge. The thermodynamics knowledge tells you that, look, this is how much is going to be your pressure and temperature, no matter what the mechanical design or the thermal design of the exchanger. The common symbol is shown here, where with that and a zigzag lines. These zigzag lines basically denote that the fluid is one fluid comes in here and goes out here, and in going so, it could be like this, that it comes in here, goes through many parallel tubes, or maybe some are in series, and then connects again and goes out. So that's a typical design of the radiator of an automobile. If you open up the hood of a car, or you look at any diesel generator set, your radiator will look like this. There's a bunch of tubes going vertically. You see a lot of fine sheet metal pieces there. That is the fins which came from the heat transfer considerations. And that whole device is basically that the hot water is flowing inside this, becoming cold, and outside this we are blowing the cold fluid, which in the case of a radiator is ambient air. So that air goes over it, and as long as the temperature of the coolant inside is more than the air temperature, it will give heat to the air, cool down, and the cold fluid will go out there. So that's a very common example of a heat exchanger. The difference is that we do not have this outside thing shown there, so we can just show like this. But if the fluid, so this fluid which goes in it, it's called the tube side fluid. It could be either the cold fluid or the hot fluid, that depends on the design. And the fluid which flows over it is generally known as the shell side. The radiator does not have, and what the shell means is that you have enclosed the other fluid also in a device, say a tank or a big enclosure. So the other fluid flows inside this and comes out. The tube side fluid goes only inside through the tubes. So when you make this entire thing, this gets known as a shell and tube heat exchanger. And this is a very, very common device used in not just power plant but refineries, practically any industry where some heating or cooling has to take place. So this is a very common engineered. So this is what happens, and the question now we'll ask, and for that we have split this problem two ways. One is the hot fluid and the other is the cold fluid. Don't mix. So what we will do in one case is to apply the conservation laws only to the hot fluid as the system. Then we'll apply the conservation laws only to the cold fluid as the system. So when we say that, I will look at first the tube side fluid, we will say that it includes all the fluid that is contained in the tube from the inlet state 1 to the outlet state 2. And so the space inside all of this is my system. So this is a tube system, and we are only going to be looking at this fluid. Once we do that, what we find that this is an open fluid coming in, going through this and exiting the system. Our system boundary ends at the outlet of this tube. The system boundary begins at the inlet of this tube. So this is an open system. So the tube side fluid is an open system. Once we do that, we now know the first next is what is the working substance that we have. Is it water, or is it a coolant, or is it some oil, whatever that may be. And then, so that tells us where to get the properties from. Once we know that this is an open system, we know that we have to write conservation of mass and then the conservation of energy, the first law, and the conservation of the entropy equation, the second law. I said this is what I need to solve. Then we make a set of assumptions which will be true for both this case. We will say that this is a flow type of a system which is open. We'll assume there is steady state. If nothing is mentioned, we will assume that. And we'll say that kinetic energy and potential energy changes of the fluid on the tube side is 0. So we put that. There's only one inlet and one outlet in the system. So this equation will become m dot 1 is equal to m dot 2. And this equation will come and say that the fluid going here, there is no work transfer on it. So W dot CV is equal to 0. And so we get the first law equation as m dot 1 H1 is related to m dot 2 H2 and Q dot CV. And in this case, we can say this is Q dot CV, tube side fluid. So everything is for the tube side. So this is one equation we have which tells us what is the relation between mass flow rate, inlet outlet enthalpies, and the heat transfer rate. Then depending on the substance that we had, if it was a vapor or a liquid, we deal it in one way. If it is a gas, it's something else. Even liquid, if we know throughout the system there is a liquid, like say water is going through it, then in both cases we will write the difference of enthalpy as Cp or Cp0 minus T1 minus T2 or T2 minus T1, whichever way that is. So we only need the constant pressure specific heat of the material. If there is a phase change, we cannot do this. Then we have to go back to H1, H2 and get H1, H2 data from the pressure and temperature at the inlet and outlet. So in the example of an evaporator of an air conditioner, you would have say subcooled, you have a mixture of vapor and liquid going in, so it is wet, so you need the dryness fraction at this point along with temperature to get specific enthalpy, and this side could be superheated vapor, in which case you need pressure and temperature here. You go to the property charts for the working substance that we have put up here and get the data from there. Cp T1 minus T2 will be a round thing. So this is what we would do for the tube side, and we could do the same thing for the other side, which you can say the shell side. Exactly the same thing. You can say that the fluid and the system boundary is from here and includes everything and ends over here. So everything contained on the shell side of this, excluding all the metal, this is our system, and the working system substance in this case. So this is also an open system where the substance coming in and going out, the system boundary ends over there and there. Working substance could be whatever. If it is say a radiator or the evaporator, the working substance will be air, or it could be water if it is a water device. And then we follow exactly the same process that we did here, get the properties, and in this case we will get Q dot CV for the shell side. And the thing that joins and completes the problem is that these two terms have to be equal, that is heat given out by the hot fluid, Q dot CV is heat transferred to the cold fluid, and these two are equal. So something that we know from experience, that m dot Cp T1 minus T2 for one substance will be equal to m dot Cp T1 minus T2 for the other substance. That comes out from this derivation. We can then go about doing all the other analysis. The only thing to remember that for liquids and gases, Cp T1 minus T2 is fine. If there is a phase change, we have to worry about getting properties from the tables. So evaporator is the case where a subcooled or a wet game, a superheated state, is the same thing as that. Saturated state becomes a liquid state, and there are devices where you could take superheated vapor and cool it to a subcooled liquid. The next thing we'll do is show these processes on one of the property diagrams. And I'm choosing to show it on the T-s diagram. So let's take the evaporator of a air conditioner. We know that there's a wet state, so the dome has to be shown on the T-s diagram. If it was on the air side, we don't need to show it. So we will say this is the tube side, which is the refrigerant, whatever that may be, say R134A, and we'll make a T-s diagram simultaneously for the outside fluid, which is the air. So in this case, what is happening is at the end of the condenser, we got slightly subcooled liquid, and this was throttled. Now, throttling is a highly irreversible process, so we don't know what states happen in between. But at the end, we know that this is enthalpy doesn't change, so it will follow a constant enthalpy line. And constant enthalpy lines on a T-s diagram look like this. So the inlet state to the expansion valve was there, and the outlet state was there. In between, we do not know what happened. The one way to show it is that we put dotted or dashed lines along this line and say, look, it is irreversible. That's number one. That's why I'm not drawing a solid line. And second, I'm superposing it on the constant enthalpy line just to tell you that this is a constant enthalpy process. But otherwise, any other line being, because it is irreversible, is fine because the intermediate states are actually not. So this is the inlet state to the evaporator. From there, it goes off there. And then what has happened here is that this phase change is constant pressure. We cannot have phase change with increasing pressure or decreasing pressure. And in all heat transfer devices, this fluid that goes through the tube, we are not doing any pumping on it. So the best and the easiest assumption is that the process throughout on either shell side or throughout on the tube side is a constant pressure process. So in this case, it will follow the constant pressure line which is there. So it will follow this and say end up over there. So the process that happens in that evaporator is like this. And we assume that the process internally is reversible. That's why we are drawing this solid line. So this was the inlet state, this is the exit state, and that is the process on the evaporator. Now what will happen on the air side? Now air side, we know that the air was warmer than this fluid at all states. So if this was say minus 10 degrees Celsius, this was say minus 2 degrees Celsius, and the air which came in was say 28 degrees Celsius and left the device at say 16 degrees Celsius. So that much temperature difference was there between the hot and the cold fluid at all times. And we know that as the air goes through it, its temperature decreases. So it started off having a temperature over there, and pressure is again constant. So we have to take a constant pressure line on this. In this case, the constant pressure lines, they look like that on the T-s diagram. The dome has not to be shown because this is not a vapor state. We are implicitly saying and assuming that air is an ideal gas. And for ideal gas, the dome is not to be shown, but we show the constant pressure lines and say now where is the inlet state? Let's say, okay, this was my pressure, this is the inlet state, this was the outlet state, and we say that this was the reversible heat transfer. So the air process was like this, the refrigerant process was like this. This gave away Q dot CV, and this took in all of that Q dot CV. Now, I made two separate T-s diagrams to clearly illustrate what was happening in both cases. And say, well, can I join these two diagrams to make one picture? The answer is yes, it is possible. The only issue is that temperature in both cases is the same scale. It's an absolute scale of temperature. So 0 for this is the same as the 0 for this. The trouble is on the entropy side. For R134A, there could be some temperature, say minus 40 degrees C, where HF or SF are taken to be 0. But for air, we could have taken some other temperature. If we reference both of these to the same value, say that look for air also, I will say that H is equal to 0 at minus 40 degrees C, or I take both of them to 0 Kelvin and say S is equal to 0, then the two scales become exactly the same, and you can join all of them together and see what the composite diagram will look like. That will be the correct thing to do. If we do not put the scales on the S and T and match it, the diagrams will be there like you see in most books, that they have said that one process is like this in the dome and the other process is like this. But strictly speaking, the entropies here do not match. This could be here, this could be here, this could be there. It doesn't matter. Okay, so the main assumption that has come out of this is that in addition to all the assumptions that we do, heat transfer processes either through heating or through cooling, we take this to be isobaric processes. That's the additional thing that has come out. And the reason is that these are substances going through a device. We are neither doing work on them, we are neither doing great expansion on it, and so the pressure in the first analysis is assumed to be constant. In the real world, if we have a system like this, like a radiator or the evaporator or the condenser, as the fluid flows through these tubes, there will be a frictional pressure drop. The outlet pressure will be slightly less than the inlet pressure, and the real engineering will have to factor that in. The data on how much pressure to mechanics or heat transfer, and that can then be put back into thermodynamics and say that in this process, if there was a pressure drop taking place, what will be the state? It will be that as it keeps going, there's a slight pressure drop all the time, it comes over there, then it would have gone along this, but there's a pressure drop, so the lower pressure isobar is there, so from here it will go and finally end up at this place. So the real substance will go like that. And the pressure here will be less than, the pressure here is less than this pressure. But in the analysis that we do, if that is not given, we assume it to be a constant pressure heat transfer process to the analysis. Okay, so that is the idea of a heat exchange.